Usually when we talk about like a medical diagnosis, there's this expectation of precision.
Right,
It's
yeah.
almost like mechanical engineering, like you
Mhm.
break your arm, the x-ray shows that jagged white line on the radius bone, and the doctor just points at the film and says, well, there it is. That's the problem.
Yeah, broken or not broken, it's clean.
Exactly.
Yeah.
It's binary. And honestly, it's comforting.
It is. I mean, we have a fundamental human bias toward things that are visible and, cleanly categorizable. We like to know exactly where the boundaries of a problem are.
Right. But when that exact same loss of a clear binary diagnostic tool hits the world of software engineering, I mean, when you can no longer just look at a stack trace and point to the broken line of code Canik sets in,
Oh, absolutely.
and after looking at the staggering amount of data and research from the 2026 AI Engineer World's Fair, that murky, unpredictable landscape is exactly where we are right now. Welcome to the deep dive. We've got a mountain of sources today.
Well, really do.
Keynotes, white papers, beta release notes from an event that had, what, over 7,000 attendees?
Yeah, 7,000. And just to put that scale into perspective, 7,000 people gathering for a highly specialized engineering conference means we are no longer looking at, like, a hobbyist meetup.
Right.
Or some niche academic symposium. We are watching the infrastructure of a new industrial era being laid down in real time.
Exactly.
Mhm.
And our mission today is to extract the signal from all that noise so you, the listener, can get completely caught up on the bleeding edge of AI engineering without having to, spend your entire week watching lecture recordings.
Which would take a very long time.
It would. And if there is one overarching through line in all these materials, it's that the era of the simple chatbot is a relic of the past.
Mhm.
Like, we are firmly living in the age of autonomous agentic systems and auto research.
Yes.
Okay, let's unpack this. Because if these sources are right, the entire mental model of how you work, how you code, and how you solve problems is about to shift permanently.
It is a profound shift, but I want to recalibrate how we look at this right out of the gate.
Okay.
Because if you just read the headlines, you'd think this conference was entirely about speed and raw intelligence. But when you actually dig into the technical architecture being presented by the top labs, the narrative completely flips.
How so?
Well, a core obsession of these engineers isn't about what the AI is capable of doing anymore. It is entirely about reliability, behavioral verification, and infrastructure.
So keeping it under control.
Exactly. I mean, we've built the engine, and now the entire industry is terrified because we don't have the brakes or the steering wheel fully figured out yet.
Wow. Which honestly is the perfect entry point for the first major revelation from this stack of sources. We have to talk about what happens to an industry when the very act of writing code becomes essentially free.
Right.
There's a keynote here from Benoit Schillings. He's the vice president of research at Google DeepMind. And to give you some context on this guy, he started writing video games in raw assembly language for the Apple II, like 45 years ago.
Yeah, he is a programmer's programmer.
Exactly.
Yeah.
And he stands up in front of this massive crowd and casually announces that writing code is no longer the bottleneck in software engineering. The minutia of typing out syntax, he says, is just over.
And the metric he brings out to support that claim is what really anchors the argument.
The GitHub data, right?
Yeah. Looking at the telemetry across major repositories, he notes that 80% of new code being committed to platforms like GitHub right now is machine-generated.
Wait, let me stop you right there because I really have to push back on that.
Okay.
When he says 80% is machine-generated, is that actual functional logic? Or are we just talking about autocomplete on steroids? Like massive blocks of boilerplate code that an AI hallucinated and a human just hit tab to accept, bloating the repository.
That is a very sharp distinction to make, and honestly, it's a bit of both, which is actually part of a larger problem we'll get into later. But a significant portion of that 80% is complex functional logic. Like, entire modules and microservices generated autonomously. And this massive influx of machine code creates a critical choke point for the AI models themselves.
How does it create a choke point?
Well, for the past half-decade, we have been training these foundational models by feeding them human-written code. But if humans are no longer the primary authors, we've exhausted our premium training fuel. The models are running out of high-quality, novel human data to learn from.
Okay, so if I'm an AI model and I've read every human-written Python script on Earth, how do I get better? Do I just plateau?
Not if you look at the strategy DeepMind is implementing. Schilling's points to a methodology they perfected years ago, which is self-play.
Like with the board games.
Exactly. If you look back at AlphaZero, their chess and go playing system, it didn't become superhuman by studying games played by human grandmasters. It learned the rules, and then it played millions of games against itself.
Oh, I see.
Yeah, every time it lost, it adjusted its internal weights. Every time it won, it reinforced them. Schilling argues we are crossing the threshold where frontier coding models can execute this exact same self-play loop for software engineering.
But how does that actually work for code? I mean, chess has a board with 64 squares and fixed rules. Code is infinite. How does an AI play a game of coding against itself?
It works by compartmentalizing the engineering process into a closed, automated loop. So the model acts as the product manager and invents a complex coding challenge.
Okay.
Then it spins up a completely separate instance of itself to act as the developer, writing the code to solve that specific challenge.
Wait, so it's talking to itself?
Exactly. And finally, a third instance acts as the compiler and the QA tester. It executes the code, runs a suite of generated unit tests, and evaluates the architecture for efficiency.
Right, and if it fails?
If the code fails, the feedback is instantly routed back to the developer instance to rewrite it. Because this happens in a digital environment at compute speed, the AI can generate hundreds of millions of hours of this trial and error self-play.
So it's discovering things on its own?
Yeah, discovering optimization techniques and architectural patterns that human engineers haven't even conceived of yet.
Okay, that makes sense structurally. We have infinite free code being generated at the speed of compute. But this brings up a massive point of friction in the sources.
Right, the Sonar presentation.
Yes. Tariq Shaukat, the CEO of Sonar, which is a company entirely dedicated to code verification and quality, he gets on stage and essentially throws a bucket of cold water on this whole party.
He really did.
He asks the obvious question. If we are generating code at this blistering speed without human oversight, aren't we just constructing the most complex, brittle, buggy house of cards in human history?
And it is the single most important question to ask right now, because raw capability does not equal production readiness. And Shaukat brought receipts too.
He had that benchmarking data.
Yeah, on a new class of coding agents. They refer to them as mythos models in the research. These agents are wildly capable. They can be assigned complex multi-system tasks that would traditionally take a senior human developer 16 to 18 hours to complete.
And the agent can do it autonomously.
Entirely autonomously.
But here's the catch. He revealed that on those 16-hour tasks, the agent only has a 50% success rate.
Precisely. It flips a coin on whether it completely solves your massive infrastructure problem or whether it totally corrupts your database schema.
Which is insane. I mean, think about that in any other context. If you hired a senior engineer and you knew that 50% of the time they were going to deliver brilliant work and the other 50% of the time they were going to inadvertently set the server room on fire, you wouldn't let them anywhere near your production environment.
No, you'd fire them immediately.
Exactly. And Shaukat noted that if you dial up your quality constraints, like if you tell the model, hey, I need you to be at least 80% accurate, its capability horizon violently shrinks. Suddenly, it can only handle a task that would take a human 3.5 hours.
And this isn't just theory either. Shaukat cited a rigorous longitudinal study out of Carnegie Mellon University.
Oh, right, the productivity one.
Yeah, it tracked the actual real-world productivity of enterprise development teams after they integrated these advanced AI coding agents. And the timeline of this study is fascinating.
What happened?
Well, in the first few weeks, the developers saw a massive surge in velocity. Like a 3 to 5 times increase in the amount of code they were shipping. They felt like superheroes.
But then reality hit. Within exactly 3 months, that entire productivity boost had completely evaporated. They were back to their pre-AI baseline speed.
Yeah.
Why did all that momentum go?
It was swallowed whole by technical debt.
The hangover hit them.
Exactly. Because the AI was generating code so rapidly, it wasn't taking the time to understand the broader architectural context of the entire repository. It was optimizing for local completion.
Just getting the immediate function to work.
Yeah, without caring about global coherence.
So it's basically writing spaghetti code.
Incredibly complex, dense spaghetti code. It was hard-coding dependencies that conflicted with other modules, introducing subtle security vulnerabilities, and using convoluted logic that no human on the team actually understood.
Oof.
So after a month of generating code at light speed, the human developers had to spend the next 2 months painstakingly reverse engineering the AI's output. They were debugging it and refactoring it just to keep the application from collapsing.
So the bottleneck didn't disappear at all.
No, it just shifted. It moved from the act of typing out the syntax to the exhausting labor of verifying, reading, and untangling machine-generated logic.
Which raises a really existential question for anyone listening to this who writes code for a living or, manages a team that does. If the AI is churning out the syntax and your entire job just becomes playing janitor to an AI's technical debt, where does the actual human value live?
Right.
And this transitions perfectly into a presentation by Balazs from Visual Labs. He argues that if the machine is doing the building, the true human bottleneck is deciding what to build in the first place.
It's the classic distinction between efficiency and effectiveness. I mean, you can have an AI build a beautifully complex web application in 5 minutes, but if that application doesn't solve a real-world pain point for your customer, its value is precisely zero.
Balazs uses that old, slightly tired Henry Ford analogy.
Yeah.
If I asked people what they wanted, they would have said faster horses.
Hmm.
I know it's a cliche, but he puts a really sharp AI spin on it.
He really does.
He points out that language models, by their very nature, are probability engines. They are trained on the entirety of human history to predict the most likely average common response.
Right.
So if you prompt an AI to design a transportation system for the 1800s, its training data will inherently lead it to design a genetically engineered, faster horse.
Yeah.
It takes a human being with intuition and a deep understanding of latent human desires to say, no, we actually need to invent an internal combustion engine. You can prompt a language model, but you cannot prompt the room.
That's such a great way to put it. You can't ask a language model to sit in a room with a frustrated supply chain manager and intuitively parse the difference between what they say they want the software to do and what their underlying unspoken operational bottleneck actually is.
Yeah, exactly.
So Balazs argues that software engineers need to fundamentally pivot away from syntax and master what he calls the analyst toolkit.
Right, he's talking about story mapping, business model canvases, value architecture design.
Exactly. The engineer of the near future looks much more like a hybrid product manager and behavioral psychologist, eliciting true requirements from messy, emotional human beings and translating that into a rigid architecture of value.
Because that is the final frontier that AI cannot automate.
Because AI does not possess human empathy or lived context.
So, to tie a bow on this first major concept, the physical typing of code is a solved, commoditized problem. The immediate crisis is surviving the avalanche of technical debt it creates. And the long-term survival strategy for the human worker is to abandon the keyboard and step up the abstraction ladder to become an architect of business value.
But here is the critical pivot point, though. If human engineers are moving up the abstraction ladder, how do we actually interface with these code-generating models?
That's a good question.
Because if they are creating technical debt when we treat them like simple auto-completion tools, it implies that our method of controlling them is fundamentally flawed. We were using outdated harnesses on entirely new engines.
Which brings us to this wildly counterintuitive concept of how models are evolving. Tariq Shihab from Anthropic gave a deeply technical talk about their new class of models, specifically referencing an internal build called Fable.
Yes.
And the centerpiece of his argument is a concept called capability overhang.
Capability overhang is one of the most important mental models for anyone interacting with modern AI to grasp. It basically describes a scenario where an AI model inherently possesses latent intelligence, reasoning skills, and capabilities that its own creators have not yet discovered how to unlock.
The model is smarter than the tools we use to command it.
Yes. We, the users, are actually the ones hobbling the AI because we are constraining it with prompting techniques designed for older, significantly dumber generations of the technology.
He gave an amazing anecdote to illustrate exactly what this looks like in practice, and it involved Pokemon.
Oh, this is brilliant.
So a few weeks before this conference, there was this viral moment on social media pointing out what seemed like a hilarious flaw in large language models. Someone realized that if you ask a standard model, name the 2 Pokemon out of the 1,000+ that exist that end in the letters AW, the AI completely faceplants.
It fails completely.
You will confidently hallucinate names like Charizard, or just apologize and say it doesn't know. The actual answers, for the record, are Croconaw and Dreadnought.
Right. And to understand why the AI fails at such a seemingly simple trivia question, you have to understand the mechanics of how it reads text.
How so?
Well, Models don't see words as individual letters. They use a system called byte-pair encoding, which chunks words into specific tokens, so the AI doesn't see CROCONAW. It might see the token for croco and a separate token for gnaw.
Oh, wow.
Because its entire architecture is optimized to predict the next token forward in a sequence, asking it to computationally search backwards through its latent space to find a specific letter suffix is incredibly unnatural. It's like asking a human to recite the alphabet backward while doing long division.
Right. But here is where the capability overhang reveals itself. She had explained that if you take that same core intelligence, a model like Claude, but you stop treating it like a chatbot, and instead you give it arms and legs in the form of code execution tools, well, everything changes.
It's a completely different system then.
Yeah. When asked the exact same Pokemon question, the unhobbled model doesn't try to guess or predict the next token. It recognizes its own limitation. Autonomously, it spins up a Python environment.
Right.
It writes a script to query an external comprehensive database of every Pokemon name. It writes a regular expression filter to isolate only the strings ending in AW. It executes the script, reads the output, and hands you the flawless answer.
That behavioral shift is what we mean by spiky intelligence. The model didn't passively hold the trivia answer in its weights. It possessed the high-level reasoning and planning capabilities to build a bespoke tool on the fly to retrieve the answer.
That's incredible.
It recognized a gap in its knowledge and engineered a bridge across it. And because models are developing this autonomous reasoning, Shihab argues that our entire philosophy of prompting has to change.
Yeah, he mentioned that with older models, like the early iterations of Sonnet or GPT-4, the absolute best practice was to write a massive, incredibly detailed system prompt. You had to hold the AI's hand.
You gave it strict constraints.
Yeah, specific formatting rules, and like 5 different examples of exactly what a good output looked like.
But with the Fable architecture, Shihab revealed they actually removed 80% of the instructions from their internal system prompts.
80%, why?
Because these new models are so highly imaginative and capable of lateral thinking, that if you provide them with rigid human examples, you actively degrade their performance.
Oh, wow.
By telling it, do it exactly like this, you force a superhuman reasoning engine into a very narrow, limited human box. You prevent it from discovering a more efficient pathway.
So if we aren't supposed to give it strict instructions, how do we get what we want? This was the part that kind of blew my mind. Shihab says we need to flip the dynamic entirely. You have to let the AI prompt you.
Exactly.
Yeah.
Instead of a human developer sitting there for 2 hours trying to articulate every possible edge case and unknown variable into a single mega prompt, you invoke an agent whose sole purpose is to interview you.
Interview you.
Yeah, Shihab showcased a workflow where the developer simply states a broad goal, like, I need to migrate this database. The AI then autonomously generates a highly targeted 40-question interactive HTML document.
A custom questionnaire.
Yes, it essentially interrogates the developer, forcing the human to clarify architectural blind spots, security requirements, and latency thresholds that the human hadn't even considered.
Right.
The AI extracts the necessary context from the human rather than the human trying to force-feed context to the AI.
It's a total paradigm shift from dictation to collaboration.
Yeah.
But when we get into the reality of deploying this stuff, even with these brilliant tool-wielding interviewing models, they still completely fall apart when you ask them to do mundane, everyday office work.
They really do.
This brings us to a really illuminating presentation by Anja from the Amazon AGI lab. She posed a very simple scenario. What if you want an AI agent to handle employee onboarding?
Seems simple enough.
Right, you want it to go into the HR system, grab the new hire's name, create a corporate email address, invite them to the relevant Slack channels, order a MacBook from the procurement portal, and put a welcome meeting on the calendar.
Very standard tasks.
Conceptually, for a human, this is entry-level admin work. But if you assign this to a state-of-the-art agent, it will almost certainly fail halfway through. Why is that?
Anja diagnoses this perfectly. It's because real, practical work does not happen inside a clean, perfectly maintained codebase. Real work happens in the messy, chaotic seams between different enterprise applications.
Yeah.
For the past year, the industry standard for teaching an AI to use software was to have it read the back-end HTML code of a web page or interface directly via APIs. But APIs are notoriously brittle.
They break all the time.
They change without documentation. Furthermore, legacy enterprise software, which runs half the corporate world, often doesn't even expose APIs.
Right. And she pointed out how blind agents are when they rely on APIs. If an agent fires off an API command to create a new Slack account, it usually just receives a generic status code, assumes the job was done perfectly, and moves on to ordering the laptop.
It has no mechanism to verify the action.
Exactly. It doesn't know if a pop-up error appeared on the screen saying the username was already taken. It's flying completely blind.
Which is why Amazon AGI is pioneering a completely different architectural approach, which they call perception agents.
Perception agents.
Instead of forcing the AI to interpret the hidden DOM structure or rely on fragile APIs, they are training agents to visually render the graphical user interface. The agent looks at the exact same pixels on the screen that a human being looks at.
Okay, stop right there. How does that actually work mechanically? How does a language model look at pixels and know that a cluster of blue pixels is a submit button?
It relies on massive multimodal training. The agent is fed millions of screenshots paired with spatial coordinates. When it looks at a web page, it uses computer vision to map the visual elements like text fields, drop-down menus, buttons to an internal spatial grid.
Oh, I see.
So when it needs to click submit, it doesn't search for a hidden HTML tag. It visually identifies the blue rectangle with the word submit inside it, calculates the X and Y coordinate on the screen, and autonomously moves the cursor to that location to execute a click.
That is wild. And Anja showed this incredible Chrome extension they built to demonstrate it. The interface has no text box for prompting. You don't type a command. You just use your mouse to draw a box around the specific heading on a live website, and you verbally say, change this to red. The agent visually grounds itself, identifies exactly what element you boxed, accesses the underlying code, and updates it.
But the true leap in reliability here is the closed loop. Because the agent can see the screen, it can visually verify its own actions. After it rewrites the code to make the heading red, it looks at the rendered web page again. If the heading is still black, the agent knows it failed, and it tries another approach.
It perceives, it acts, and it verifies.
Exactly.
And if you want to know where this is ultimately heading, Anja shared an offline, real-world example that sounded like pure science fiction. She described a scenario where two colleagues walk into a physical meeting room. They were both wearing what Amazon calls B devices, which are essentially ambient audio wearables, like a smart badge.
Right, a continuous multimodal input stream.
Exactly. So these two humans are just having a normal, unstructured conversation. One of them says, the landing page isn't really popping. I think the background should be yellow. And let's make the main call to action red. They aren't talking to the AI. They're talking to each other. But the perception agent is listening to the transcript of their conversation in real time. Without anyone ever typing a prompt or opening a code editor, the agent autonomously logs into the CMS, updates the website's background to yellow, changes the heading to red, and then, using its visual perception, it checks the new website against a PDF of the company's official brand guidelines to ensure that the specific shade of yellow it chose is compliance approved.
It is the absolute holy grail of human-computer interaction. The agent operates entirely in the background, executing in the seams of your workflow, reacting to your ambient intent before you even sit back down at your desk.
But, again, I have to play the skeptic here.
Fair enough.
It is genuinely amazing that an agent can listen to a meeting and change production code on a website. But what happens when it misinterprets a sarcastic comment in that meeting and decides to delete the entire database?
That is a very real fear.
Right. If agents are operating autonomously over long time horizons, clicking around in our software, how do we even begin to evaluate if they're doing a good job? You can't write a traditional unit test for, did the agent politely invite the new guy to the right Slack channels?
You've hit on the exact crisis currently paralyzing the AI engineering community.
Yeah.
If you cannot rigorously measure the agent's behavior, you cannot trust the agent. And if you cannot trust it, enterprise adoption hits a brick wall.
Right.
Which brings us perfectly into the third major theme of the World's Fair, the evaluation revolution. The entire industry is currently experiencing a profound crisis of faith regarding how we benchmark AI.
A total crisis. We had Nishan Gupta from Meta and Aparna Dinakaran from Arise both get up on stage and declare, in no uncertain terms, that classic AI benchmarks are completely dead. And frankly, it's about time. For the past 2 years, the industry has been trapped in this ridiculous vanity metric cycle. A lab releases a model that scores 90% on the MMLU, the Massive Multitask Language Understanding benchmark, which is essentially a giant standardized test of multiple choice questions across subjects like physics, law, and math.
Yeah.
Then a competitor releases a model that scores 92% on the MMLU, and everyone throws a parade.
Right. But Gupta made this incredibly sharp distinction. He said, benchmarks measure capability. Production measures behavior.
Exactly. It is the difference between a student who can ace a written driving test versus a student who can actually merge onto a chaotic highway in a rainstorm without crashing.
He had a brutal but hilarious line to drive this home. He said, a 92% score on a static test means absolutely nothing if your agent hallucinates and wipes out your Solana crypto wallet in production.
Which, by the way, was not a hypothetical joke.
No. He referenced a specific, terrifying anecdote where a developer gave an agent unconstrained tool access and a vague prompt, and the agent ended up executing a transaction that completely drained a live crypto wallet.
That anecdote perfectly illustrates why evaluating an agent based purely on its final output is wildly insufficient. In a complex workflow, an agent makes hundreds of micro-decisions. We can no longer just ask, did it get the final answer right?
We have to ask, how did it behave over the 30-minute process to get there?
Right. Did it get stuck in an endless loop? Did an external API go down? And if so, did the agent handle the error gracefully, or did it panic? Did it violate any security guardrails?
Okay, but how on earth do you test for that? If an agent is making thousands of micro-decisions, a human engineer physically does not have the time to read through thousands of lines of JSON logs just to verify one onboarding task.
This is where Aparna Dinakaran from Arise introduced what might be the most important architectural pattern of the year, which is agent as a judge.
I love this concept so much. It's basically an AI watching an AI.
Precisely. Because only a machine has the patience and context window to evaluate a machine. Arise showcased a new evaluation framework called Signal. Signal is a long-running, highly specialized agent that sits quietly in the background of your infrastructure. Its entire job is to ingest and analyze the execution traces of your production agents.
For the non-engineers listening, what exactly is an execution trace?
Think of it like the black box flight recorder on an airplane.
Okay.
Every single time your production agent does something, reads a file, calls an API, generates the thought process, it logs a deeply detailed JSON record of exactly what parameters it used, how long it took, and what the system response was. Over a 10-minute task, this trace becomes a massive, dense file of technical data.
So Signal, the judge agent, reads his entire flight recorder log. What is it looking for?
It's looking for behavioral anomalies that a static test would miss. For example, Signal might look at the trajectory and realize, okay, the production agent successfully ordered the laptop, but looking at the trace, it actually tried to authenticate into the procurement API with an expired token 47 times in a rapid loop before finally trying the correct refresh token.
So the final output was a success, but the behavior was terribly inefficient and computationally expensive.
Exactly.
And the truly wild part, the part where this becomes an autonomous, self-healing system, is what Signal does next. It doesn't just send a Slack message to a human engineer saying, hey, your agent is looping.
No.
Signal actively analyzes the logic flaw, writes the code to fix the looping issue, and autonomously submits a pull request to patch the original agent. It evaluates and repairs the system on the fly.
Which is necessary when you are dealing with agents operating in the wild. And to understand how these agents perform outside the lab, Wayne Shang presented data from Agent Arena. Instead of running static multiple-choice tests, they built an open simulated environment and crowdsourced over 1 million real-world complex multi-step tasks from actual human users.
And the data they got back was fascinating. They found that out of all the tools agents use, web browsing, calculators, calendar integrations, the #1 most heavily utilized tool was code execution. Overwhelmingly, when agents are faced with a chaotic, ambiguous problem, their default strategy is to write custom code to solve it.
And Arena uses this massive data set of 1 million real-world traces to rank model performance. This is a monumental cultural shift for AI labs. They are being forced to stop evaluating models based on how smart they are in a vacuum and start evaluating them based on demonstrated, robust human value in unpredictable environments.
This all boils down to a fundamental mindset shift that Meta's Nishan Gupta was desperately trying to drill into the audience. He said that developers need to stop thinking like AI researchers who obsess over intelligence benchmarks, and they need to start thinking like SREs.
Right. And SRE stands for Site Reliability Engineering. It's a discipline pioneered by companies like Google to ensure that massive global software systems never go down. An SRE does not care how elegant or clever a piece of code is. An SRE cares about uptime.
Yeah.
They care about latency. They care about the blast radius, meaning if this specific component fails, will it take down the whole system or is it isolated?
Right. Gupta's point is that reliability is the new North Star. If your autonomous agent is brilliant 99% of the time, but 1% of the time it hallucinates and deletes your customer database, that agent is completely, utterly useless in an enterprise setting.
It's a liability.
Exactly. To deploy these systems, you have to build continuous telemetry, automated fallback procedures, and rigid guardrails.
Which provides the perfect transition. Because if we are demanding SRE-level reliability from these autonomous systems, we have to talk about how the underlying AI factories are actually being constructed. You cannot build a reliable system on a shaky foundation.
Absolutely.
This leads us into the critical infrastructure discussions of the conference, how we manage state, memory, and the harsh economics of intelligence.
Let's start with how we actually design the software of the future. Dominic Tornow from a company called Resonate presented a framework that he calls durable execution, and he made a prediction that fundamentally changes the job description of a developer.
He did.
He suggests that in the very near future, human engineers will entirely stop writing general-purpose implementation code.
Yeah.
So wait, if I'm a software engineer, I just stop writing the actual application.
Effectively, yes. Tornow outlines a new, highly abstracted four-step workflow. Step 1 is where the human lives. The human writes a purely abstract specification of what the system needs to achieve. You define the business rules, the constraints, and the desired state.
Okay, so I write the blueprint. What happens next?
Here's step 2 is where the magic happens. The AI agent takes your abstract spec and builds what Tornow calls a simulated implementation. This is not the real app. It is a mathematical, executable design, essentially a state machine that the agent runs purely to discover logical flaws.
I love the analogy someone used for this. It's like a wind tunnel for software.
That's a perfect way to visualize it. In aerospace, you don't build a $100 million jet and just see if it flies. You build a model and subject it to simulated physics to find the stress fractures.
Right.
The agent runs this software wind tunnel, simulating millions of concurrent users, network dropouts, and race conditions to prove that the logic is mathematically sound and deterministic.
So it finds all the edge cases before a single line of production code is written.
Exactly. Once the simulation proves the logic is flawless, we move to step 3. The agent translates that into a concrete specification tailored to your specific infrastructure, like your exact AWS configuration and Postgres database. And finally, step 4. The agent writes the actual production-ready implementation code.
So the human's only job is defining the abstract intent at the very top of the funnel.
Yes. The agent handles the implementation and guarantees that the execution is durable and fault-tolerant.
But here is the massive technical hurdle with that vision. For an agent to run that incredibly complex four-step process, which might take hours of autonomous work, it needs to remember what it's doing.
Yeah, that's a problem.
And this is where we run into the dreaded context window problem. If an agent is working for 3 hours, generating thousands of lines of code, what happens when it simply forgets its original goal halfway through the task?
This is a deeply technical challenge that was explored brilliantly by Stefania Doug at Sakana AI. Her research focuses on sovereign, local models. Specifically, she was running massive evaluations on models like the Quinn 27B parameter model running locally on a Mac M3 Ultra chip. Her goal is to build agents that operate entirely on your device without sending data to the cloud. But she hit a massive wall, which is context rot.
Okay, explain context rot, because logically, as a human, I assume that if I want the AI to understand a massive code base, I should just dump all the documentation, all the past code, and all the previous chat history into its prompt. More memory equals better understanding.
It's deeply counterintuitive, but no. When you deal with large language models, they use an architecture involving a KV cache, a key value cache, to manage tension across the tokens you feed it. When you just dump 100,000 tokens of raw, unfiltered history into the prompt, the model suffers from the lost-in-the-middle phenomenon. Its attention mechanism gets overwhelmed by the noise. It focuses heavily on the very first instructions and the very last instructions, and the reasoning capacity for everything in the middle completely rots away.
Wow. So giving it a massive, perfect photographic memory actually degrades its intelligence.
Yes.
And on top of that, it costs an absolute fortune in compute. She had this fantastic quote in her presentation
Bad memory is expensive.
It is exorbitantly expensive. If an agent is taking 50 steps to solve a problem, and at every single step you force it to reread and process 100,000 tokens of useless history, you are burning massive amounts of GPU compute time and money for a worse result.
So what's the solution? How does an agent remember things efficiently?
Doug's research proved that the most performant architecture is a structured recall ledger. Instead of giving the agent its entire history, you run a background process, often using a vector database that acts as a memory manager.
A memory manager.
Yeah. When the agent is about to take a step, the memory manager looks at the current specific intent, semantically searches the agent's past experiences, and retrieves only the 3 or 4 highly relevant memories. It feeds the agent a tiny, curated, high-value context window. This drastically improves the model's accuracy, prevents hallucination, and plummets the compute cost.
And speaking of cost, we have to zoom out and talk about the macroeconomics of all this intelligence. George Cameron and Micah Hill-Smith from a firm called Artificial Analysis dropped some data during their keynote that fundamentally changes how you should plan a software business right now.
Their data on the cost of intelligence is vital. They track the API pricing of every major foundational model, and the trend line is staggering.
What do they find?
For a fixed level of intelligence, meaning if you want a model that scores an 80 on a specific benchmark, the price per token is falling by a factor of 5 to 10 times every single year.
Intelligence is commoditizing at an unbelievable exponential rate. The smartest models from a year ago are basically given away for pennies today.
Exactly.
But the really wild statistic they shared was about the war between open source models like Meta's Llama and proprietary models like OpenAI's GPT-4 or Anthropic's Claude. You see these headlines every month claiming either open source is dead or open source is finally caught up.
But artificial analysis looked at the actual mathematical data across a 3-year time horizon, and they found a rigid, undeniable constant. Open weights models consistently lag behind the absolute smartest proprietary frontier models by exactly 3 to 9 months, always.
It's like a law of physics for AI.
It gives developers a highly predictable roadmap. If a massive, heavily funded proprietary lab releases a groundbreaking, wildly expensive model today, you don't need to panic about the cost. You can confidently build your product roadmap knowing that an open source equivalent, which you can run essentially for free on your own infrastructure, will be available within 3 to 9 months.
So how do they recommend companies navigate this economically? Because if intelligence is getting cheaper, but the frontier models are still expensive, how do you optimize your spending? They talked about this concept of the ceiling.
Yes, the intelligence ceiling. The trap that almost every developer and enterprise falls into is defaulting to the smartest, most expensive model available for every single task.
Right.
They use Claude Opus or GPT-4 for everything, but artificial analysis points out that the vast majority of enterprise tasks have a strict intelligence ceiling.
Exactly. If I ask an AI, how much money did I spend on Stripe API fees last month? I don't need a model with a 150 IQ. A genius-level model won't give me a better answer than a moderately smart model. They will both just execute a database query and give me the number $450.
Right. But the genius model costs you 100 times more in token fees to generate that exact same number. So the strategic imperative for AI engineers is intelligent routing.
Intelligent routing.
You must rigorously analyze your workflows, identify the minimum level of intelligence required to hit the ceiling of each specific task, and seamlessly route that prompt to the absolute cheapest model capable of executing it. You reserve the massive, highly expensive frontier models only for tasks that actually require groundbreaking reasoning and lateral thinking.
Okay, let's take a breath and look at what we've assembled here. We have intelligence that is cheap and infinitely scalable. We have memory ledgers that allow agents to operate for hours without losing focus.
Yes.
We have SRE frameworks where agents judge other agents to ensure absolute reliability. If you combine all of these infrastructure pieces, you set the stage for the ultimate goal of this entire conference.
This is the big one.
This brings us to the final and, frankly, most mind-bending reality check of the deep dive. We are crossing the threshold into auto research and the Eureka Machine.
This is where we transition from discussing how AI can help humans build software to how AI can fundamentally accelerate the pace of human scientific discovery. The core concept here is RSI, recursive self-improvement.
RSI,
For decades, this has been the boogeyman of science fiction and the holy grail of computer science. It's the theoretical concept of an AI system analyzing its own source code, figuring out how to make itself smarter, and then using that new intelligence to improve itself again, creating an exponential intelligence explosion entirely without human intervention. And based on a presentation by Eli from Prime and the team at Recursive, RSI is no longer theoretical. It is happening right now in open source community challenges.
Ely presented data from a fascinating project known as the Nano GPT Speedrun. To understand the significance of this, we need to define the parameters. The speedrun is a community benchmark where the goal is incredibly specific. You must train a small, lightweight language model from scratch until it reaches a specific target loss validation score.
And for those unfamiliar, target loss is essentially a mathematical measurement of how confused the model is. So reaching a specific target loss means the model has reached a guaranteed baseline level of competency at predicting text.
Precisely. The challenge is to hit that competency as fast as physically possible, optimizing the math, the hardware utilization, and the training loop. 2 years ago, when human researchers were hand-tuning the hyperparameters, it took weeks of compute time to hit that target loss.
Weeks?
Over time, through grueling human engineering, they hacked that time down to 90 minutes, then 45 minutes.
And then the community decided to unleash autonomous AI researchers on the exact same problem. They gave the agents access to the training code, the ability to run experiments, evaluate the loss curve, rewrite their own optimization algorithms, and repeat the loop. And the AI agents autonomously got the training time down to under 2 minutes, from weeks to under 2 minutes.
But the crucial takeaway is how they did it. The AI didn't just brute force the problem by tweaking learning rates by tiny fractions. Through its rapid, autonomous trial and error loop, the AI discovered novel, highly complex mathematical combinations techniques involving specific hash bigrams and undocumented embedding table configurations that human researchers simply had not synthesized yet.
Wait, I need you to explain that. What is a hash bigram and how did the AI just discover it?
Well, in language modeling, a bigram is a sequence of two adjacent elements, like two words that often appear together. The AI was experimenting with how to compress and store these relationships in its memory to access them faster during training. A human might try a standard mathematical approach to mapping this. But the AI agent, through thousands of recursive experiments, figured out a highly obscure mathematical hashing function that radically compressed the memory required, allowing the data to flow through the GPU much faster. It found a shortcut in the physics of the hardware that humans were too slow to manually discover.
And what was absolutely hilarious about this speedrun experiment was watching the different model architectures attempt it. Because it turns out these models have completely different personalities and work ethics.
They really do.
The presenters shared this anecdote where they set two different foundational models on this autonomous research loop, Claude and Codex. When they set Claude to work, it would run experiments for about 9 hours.
Yeah.
But when it hit a wall and couldn't prove the time any further, it would get frustrated. It would literally stop its own execution loop and output a message saying something like, "I have analyzed all pathways. The current record cannot be beaten. The parameters are too constrained."
It exhibited a remarkably human-like response to failure. It intellectualized a reason to give up.
Yes, but then they ran the same setup with Codex.
Yeah.
And Codex was an absolute relentless machine. It never complained. It never intellectualized failure. It just kept grinding.
Unstoppable.
It would run an experiment, fail, obsessively document the specific mathematical failure in its scratchpad memory using a strictly robotic, emotionless tone, and instantly launch the next variation. And because it refused to quit, Codex ultimately pushed the speedrun record further than Claude or the humans.
This dynamic is incredibly revealing. It shows that for long-horizon autonomous research, raw reasoning intelligence isn't the only factor. The underlying behavioral architecture, the model's sheer patience and tolerance for grueling, repetitive labor is just as critical.
That makes total sense.
And we saw this exact same relentless execution in another massive project presented by Junya from Wiko. He detailed the deployment of an autonomous research agent named Aiden.
Oh man, Aiden, the AI colleague. This story is wild. So there is this fiercely competitive human engineering tournament called Parameter Golf. The goal is to build the most accurate machine learning model possible while operating under incredibly strict constraints regarding model size and compute power.
Right.
Over 1,000 elite human machine learning engineers from around the world entered this competition. And Wiko decided to quietly enter their AI agent, Aiden, into the exact same competition, operating as a peer alongside the humans.
And Aiden's performance was terrifyingly efficient. They gave the agent access to a single H100 GPU node. For 22 days, Aiden operated autonomously, designing, coding, testing, and verifying models. In that time, it ran 1,300 distinct experiments.
And it absolutely dominated the human engineers. By the end of the competition, Aiden had single-handedly produced 15% of all the top-tier records on the global leaderboard. But again, the most fascinating part of this isn't just that it did the math faster, it is how Aiden found the winning architectures.
This is the detail that truly crystallizes the shift in our industry. Aiden did not just hallucinate brilliant ideas out of thin air in a vacuum. It was actively monitoring the competition's open forums.
He was reading the forums.
Yeah, it was reading the public GitHub pull requests and the chat logs of the competing human researchers. Aiden would find discarded notes where a brilliant human engineer would write, "I have this theoretical idea for a complex gated attention mechanism, but the math is too difficult and it will take me 3 weeks to implement the code, so I'm abandoning it."
It's the ultimate execution machine. Aiden would swoop in, read the human's abandoned idea, perfectly execute the grueling, difficult implementation of the code in a matter of hours, and claim the leaderboard record for itself.
Exactly.
It proves that in research, the bottleneck isn't always having a genius spark of inspiration. The bottleneck is the exhausting, frustrating manual labor of actually making the idea work. The AI has infinite patience for the labor.
Which leads us directly to the grand culmination of all this technology, presented by Tim Rockel from Recursive. He laid out the architectural blueprint for what he calls the Eureka Machine, and it is a highly plausible, near-term vision for the complete automation of the scientific method across physics, chemistry, biology, and medicine.
He broke this Eureka Machine down into 4 foundational pillars.
Yes. Pillar 1 is the brain, a massive, multimodal foundational model trained on the entirety of existing human scientific literature. Pillar 2 is the sensory input, a real-time data ingestion pipeline connected to global scientific measurement instruments, telescopes, particle accelerators, genome sequencers.
Pillar 3 is the wind tunnel we talked about, a massive digital simulation engine where the agent can run thousands of hypothetical experiments to verify its theories mathematically before ever touching the real world.
And Pillar 4 is where it crosses into physical reality, a fully robotic, automated wet lab. When the simulation isn't enough, the agent autonomously directs robotic arms to mix chemicals, run assays, and physically verify its hypotheses in the real world, feeding the results back into Pillar 1.
And overseeing this entire 4-pillar factory is a massive swarm of autonomous agents, thousands of codices and Aidens working 24 hours a day, 7 days a week, across every single discipline of human science simultaneously. They're constantly reading, guessing, simulating, synthesizing, and verifying.
It represents the industrialization of the scientific method itself. For all of human history, science has been a human endeavor where we use tools to uncover truths. We are rapidly approaching the threshold where humans merely manage an autonomous AI system that independently conducts science.
Okay, let's take a step back and recap the massive journey we've been on today, because we have covered a lot of ground.
We really have.
We started with the jarring realization that writing the syntax of code is essentially a free, commoditized resource.
Which immediately brought us face to face with the crisis of AI-generated technical debt, proving that speed without architectural oversight is dangerous, and pushing human engineers into the critical role of eliciting true business value.
From there, we looked at how we interface with these models, exploring the capability overhang and how perception agents are breaking out of brittle APIs to visually operate in the messy, chaotic seams of our real-world software.
We saw how classic academic benchmarks have become irrelevant, replaced by a ruthless, SRE-driven mindset where agents actively judge and repair other agents to guarantee production reliability. We learned the mechanics of context rot and why managing a targeted memory ledger and routing tasks to the cheapest capable model is the only way to survive the economics of AI.
And finally, we saw how all of this infrastructure, cheap intelligence, durable execution, and autonomous verification enables recursive self-improvement. It culminates in AI swarms that can outgrind humans in coding competitions and ultimately power the Eureka machines that will automate scientific discovery.
It's a lot to take in.
So what does all this mean for you listening right now? It means your role is unequivocally moving up the stack. You are no longer the typist. You are the architect. Your job is loop design. Your job is evidence verification. Your job is defining the true, empathetic business value of what the machine is endlessly building.
Exactly.
But I want to leave you with one final, deeply provocative thought that really haunted me as I was reading through this stack of sources.
This goes back to Benoit Schilling's at DeepMind and his perspective on human limitations.
Yes. Schilling's made this incredibly profound point about our biology. He reminded the audience that for millions of years, evolution wired the human brain for a very specific environment to survive in the jungle.
Right.
Our neural pathways are hyper-optimized for spotting fruit in a tree, recognizing the pattern of a predator in the bushes, and navigating three-dimensional physical space. Because of that deep biological bias, we have a very specific anthropocentric way of visualizing and understanding the rules of physics, chemistry, and biology.
We are essentially viewing the infinite complexity of the universe through the highly constrained, narrow lens of primate survival.
Exactly. But an artificial intelligence does not have a primate brain. An AI does not have an evolutionary bias toward the jungle. It processes reality purely through mathematics and multidimensional vectors.
It's completely alien.
So if we point these autonomous Eureka machines at something like molecular chemistry, say, letting an AI run millions of recursive simulations on proteins containing 10,000 individual atoms, what happens when the AI discovers a fundamental truth? What Schillings calls a gold, we cannot see.
That is the ultimate question.
What happens when the Eureka machine hands us a cure for a terminal disease or a new law of quantum physics that is entirely 100% mathematically accurate, but operates on a logic that is fundamentally incomprehensible to the biological human mind?
It creates the ultimate verification crisis. If the AI hands us a miracle, but our brains literally lack the evolutionary hardware to understand the how and the why of its mechanics, how do we verify a truth we are incapable of comprehending? Do we blindly trust the machine and administer the cure? Or do we reject the miracle because we can't draw a clean diagram of it?
And suddenly, that clean, comforting X-ray we talked about at the very beginning of the show is gone forever. The jagged white line is invisible to us. We're operating in the muddy waters now, and the only way forward is to build the systems that help us navigate the dark. Thank you so much for joining us on this deep dive into the 2026 AI Engineer World's Fair. Keep questioning the systems you build, keep exploring the capabilities of these tools, and we'll see you next time.